How are you doing tonight?
Good. How are you?
Good. Is your spring break next week also?
Yes, it starts on Wednesday.
Okay, so are you looking at a test tomorrow?
I have a quiz tomorrow and a test on Wednesday.
Okay, cool. Well, I'll be around next week if you need any sessions on Monday or Tuesday.
Okay, that's good.
What do you want to do tonight?
I'll send it to you actually.
Okay.
One moment.
Okay. This is a night that I'm happy to be doing online tutoring because it's snowing out.
Oh, that's not good.
Well, it's great as long as I'm doing online tutoring.
Yeah, true.
It's not very good if I got to drive out to do it, but
Mm-hmm.
this online tutoring is pretty good stuff.
Yeah, it's very helpful. So that I don't have to leave the house and go places.
Yeah, technology is terrific.
For sure.
All right, I got it here. I have been notified that I have to upgrade my operating system by April 1st for GoToMeeting. They're not supporting Windows Vista anymore. So,
Yeah, I heard about
yeah, so I'm going to do it next week during spring break. I'm always expecting problems, you know.
that.
All right, let's see. Use the following function. All right. Shall we start with 1?
Yes.
Okay. First of all, in these functions, always factor if you think there's a possibility that one of the factors might cancel with the denominator.
Thanks.
That's the top. That's the bottom factor. Taylor?
Yes. Oh, sorry.
How does the bottom factor? In other words, if I want
X
to
plus
factor
3,
and
X plus 3, and X minus 1.
all right. So that's really what we're looking at. What two values can X not be?
X plus 3.
It can't be minus.
X minus 3 and X minus 1.
No, plus 1. In other words,
Plus 1.
remember what's going on here. We cannot divide by 0. So I cannot have that being 0, and I cannot have that being 0. Well, what would make those 0? An x of 1 would make that 0, and an x of minus 3 would make that 0. So that's always the first rule of mathematics, is make sure you don't divide by 0. Okay? Now, in point of fact, that x plus 3 will cancel with that x plus 3 to make the function look like this, but it does not alleviate the domain restrictions. In other words, that domain restriction that x cannot be equal to minus 3 still holds. Obviously, it can't be equal to 1 also. But even though we've reduced the function to this, the original domain restriction holds. Okay? So this is f of x. What's the domain of this?
The domain would be negative infinity to negative 3. Union. -3 to -1.
To 1.
Union.
Not -1, 1.
Or to 1, yeah, to 1. And then union 1 to infinity.
Okay. Okay. Vertical asymptotes. Where do we have a vertical asymptote?
Do you do vertical asymptotes by plugging in or dividing?
Again, division by 0 rules everything.
Okay.
However, that original restriction that x cannot be equal to -3 because of this denominator, that no longer is a vertical asymptote. It does become a hole. And that's what it's called, is a hole. Okay? But we still have a vertical asymptote at x equal 1. Because when I look at that function right there, x cannot be equal to 1 ever, and it's going to produce a vertical asymptote at x equal 1, right there. And we have, let's go ahead and put it.
Why can it never equal 1?
Well, because that would make the denominator 0.
Okay.
We have a hole at x equal -3 because that's still a domain restriction left over from the original function.
Okay. Now I see what you mean.
Okay. Horizontal asymptotes. Now for horizontal asymptotes, I really can just work with the final function here. I don't need to go back to the original one. I could. Horizontal, what happens when the degree of the numerator is the same as the degree in the denominator, the maximum degree, which would be x squared here, x squared there, or if I go to my most recent function, it's x and x.
So it'll be 1 over 1.
Correct. So the horizontal asymptote is at y equal 1. So let's draw that in there.
So whenever you do that, it's a over b pretty much?
No, it's the ratio of the coefficients. A over b sounds like you've been doing conic sections. But this is not a conic section. This is just a rational quotient. And whenever the highest degree in the numerator is the same as the highest degree in the denominator, the horizontal asymptote is the ratio of their coefficients, which in this case is 1 over 1. Okay?
Okay.
If that was a 2, the horizontal asymptote would be at 2. The ratio of the coefficients, if that was 2 and this was 5, the horizontal asymptote is at 2/5.
Okay.
Okay. And let's see, X-Intercepts. Whenever we're trying to graph these kind of hyperbolic functions like this, the very first goal is to lay down your grid, which is your vertical and your horizontal asymptotes. Because we know this thing is hyperbolic in nature. In other words, it's going to look something like that. You know what hyperbolas look like, right?
Yes.
Okay. So it's either going to look like this, or maybe we'll be in this quadrant and this quadrant. We still have to determine that. But the next question they want to know is X-intercepts. So how do I solve for that?
If I remember correctly, do you use the what's the name? Do you equal something to 0?
Well, a really important concept in math is that X-intercepts occur when y equals 0, right?
Yes.
And y-intercepts occur when x equals 0.
Equals 0.
So if I want to solve for x-intercepts, starting here, I'm just going to turn that to a 0. In other words, I'm letting y, or f of x, they're the same thing, equals 0. Where is that equal to 0? In other words, how do you solve that right there?
It would have to be a 3 and a 1, and it would be 3.
Just x equal 3. I don't care about the denominator. The only way this rational quotient is equal to 0 is if its numerator is equal to 0. So if I set x minus 3 equals 0, x is 3. Okay, well this is x is 1, so I have an x-intercept right there. My graph's going to cross the x-axis right there and only there.
Okay.
Okay, so x-intercepts at 3. About y-intercepts. In other words, the more parts of this graph we can put before we draw it, the more we'll know about how to draw it. Well, we know now the grid we're going to use. We know that it has to cross somewhere down here, and now we're looking for where it might cross the y-axis. Well, remember what I said is that the y-intercepts come when x is 0. So where's the y-intercept on this?
When you plug in 0 for everything?
Just x, not everything. X.
That would be -3 over -1, which is 3.
Okay, so there's the y-intercept right there. Okay, now that gives me a real good idea that I'm in this quadrant here and this quadrant here for my hyperbola. Okay, if I had any question about it, I would plug in a number greater than 1. And see where I ended up on the x-axis. In other words, greater than 1 because this vertical asymptote is at x equal 1. So I know that if I plug in x equal 2, that'll tell me where I'm at, right?
Yes.
So if I plug in x equal 2, I get -1 over 1. So when x is equal to 2, y must be -1. I'm down in this quadrant again. So now that's even more confirmation that my hyperbola is looking like this. And as long as it's a hyperbola like this, it's only going to have 4 quadrants. And so you know the other end of it is diagonal to it, especially knowing that I have a y-intercept right there. So that's my graph, except for one thing. What did I leave out?
The holes?
The hole. The hole occurs at x equal -3. There's only one hole. X equal -3 is about there, so I have a hole right there. In other words, x is never allowed to be equal to -3.
Okay.
Now, if I were to graph this on Wolfram alpha, you would not see the hole. Why? Because it's infinitesimally small. It's only at -3. It's not at -3.1. It's not at -2.9. It's at 1 point only. I'm never going to see it on a graphing calculator or Wolfram alpha. So you have to know that it's there.
Okay.
And we typically do put it in as an open hole, and we now can interpret this graph properly. But if I were to do it on Wolfram alpha, I could not. Okay, so I guess we've done everything on this. We've calculated everything they wanted, and we've graphed it. They didn't even ask us to graph it, but we did anyway.
Okay.
All right. Number 2. It asks us to graph it, show the asymptotes, the intercepts, and the holes. We did all of that already.
Yeah.
Describe the vertical asymptote of that graph using limit notation. I'm not sure what they mean by that.
It's like where it's like a limit of x to whatever is like where, for example, it would be like
Okay, I think
limit x.
let me tell you what I think they mean, and you tell me if this is
Okay.
correct. Okay, this y was originally f of x. Okay, we're going to go back and put that in there. I think what they mean by that limit notation, actually I'm surprised you're getting this already, but if I want the limit of f of x as x approaches equals what? What would x approach? It would approach 1 from the left side. Have you had limits right and left approaches?
Yes.
Okay. What is the limit of f of x as x approaches 1 from the left side?
Would it be negative infinity?
Positive infinity.
Or what?
Positive infinity.
Positive infinity.
In other words, this is where we're at right here. If
Yes.
I'm going along the x-axis approaching this vertical asymptote at 1, I'm approaching it from here. I'm approaching it from the left side. It goes all the way to infinity.
Okay.
And what is the limit of f of x as we approach 1 from the right side?
Negative infinity, because it goes down.
Correct.
Yeah, that's exactly what it is.
The way we do these limits as we approach from the left and the right is basically get on the x-axis. If we're approaching from the right, we're going like this. I mean, if we're approaching from the left, okay? If we're approaching from the right, we're going like this. So just choose whatever direction you're referring to there, and you can see the answer. You can read it right off the graph.
Oh.
I didn't realize you had gotten into limits, especially left and right limits.
Yep.
That's true pre-calc. Actually, that's calculus. No, that's calculus. The difference between calculus and all other math that precedes it is the concept of limits. So the moment you start talking about limits, you're talking calculus. Describe the horizontal asymptote using limit notation. And there is a horizontal asymptote here. So here, it's going to be a little different. We're not looking at the limit of f of x. We're looking at... Actually, we are. My mistake. My mistake. We're looking at the limit. I'm going to erase this just so we get it all on the same page.
Okay.
I'm looking at the limit of f of x. Horizontal asymptotes mean as x goes to infinity or as x goes to negative infinity. That's what your horizontal asymptote is always. So I'm going to say the limit of f of x as x goes to infinity is what?
1.
What is that horizontal asymptote? Oh, it is 1. Excuse me. Yes. My error. That's the same thing as end behavior. The end behavior on this function is what the function approaches as we approach the horizontal asymptote. That's what end behavior means. And clearly it's headed towards 1, right? And it's headed towards 1 whether we're going from negative infinity or positive infinity. So 1 is the answer for both of them.
Oh.
Make sure you understand that. In other words, in the one case, as x was approaching 1, but in this case, we got x approaching positive infinity and x approaching negative infinity. And it still goes to 1, but it's not the vertical asymptote, it's this asymptote that it's approaching. So if that asymptote happened to be at 4, it would be going to 4. Okay? I hate the fact that they put the vertical asymptote at 1 and the horizontal asymptote at 1. It's confusing.
Yeah, it is.
Well, and it doesn't need to be. You could use different numbers.
Okay.
All right, so that answers 4. All right, same thing for this. This is good. I like the fact that they gave us a very similar problem. Almost no difference whatsoever. What's our first step?
The first step, I would be looking for the domain, so I'd factor. Okay. So x minus 4 and x plus 4.
That's always the first step, whether you're searching for domain or not. You always want to break these down because it really makes a difference in the vertical asymptotes.
True.
So how does this factor?
X minus 4 plus 1, or x plus 1.
Yeah. Okay, so our domain is what?
Our domain would be negative infinity to negative 4.
Not negative 4. Remember, it's what makes that 0.
Yeah, never mind.
Positive 4. That's a very common mistake. Just make sure you're catching it. In other words, you're looking at a linear factor here, but what makes this equal to 0 is an x of positive 4, not an x of negative 4.
Because the negatives get crossed out.
Well, when x is 4, this is 0. Remember, everything hinges on what we cannot have a denominator be 0. That's what everything hinges on.
Okay. So then that would be 4, and then 1.
Not 1. What makes that 0?
Negative 1.
Negative 1.
But I thought you said the denominator can't be 0.
It can't. That's why there's a parentheses next to that.
Okay.
Because our allowable domain, I can go, hold on, I made a mistake here. I didn't make a mistake, but we got it backwards. We always want our domain in interval notation to start at negative infinity and move to the right.
Negative 1.
So the first point we reach is minus 1.
Okay.
And then the next interval is minus 1
4.
to 4. And what's the final interval?
The final interval would be 4 and infinity.
Okay. So that's the domain. I can basically be all real numbers except x equal to 4 or x equal to minus 1.
Okay.
Okay. Now, let's go and work on this function. I can cross off that x minus 4 and that x minus 4. So the function turns into x plus 4 over x plus 1, but it's not quite that. It's not exactly the same as that, because we still have this domain restriction. I still cannot have x equal to 4. Okay?
Okay.
It's not because of this 4 in the numerator. It's because of this 4 over here.
Okay.
Okay? So, vertical asymptotes. Now, to get vertical asymptotes, we're going to look at this function right here only. To get holes, we'll look at the original function. But to get vertical asymptotes, you always go from the function you end up with after factoring and canceling. So where's my vertical asymptote?
The vertical asymptote would be at -1.
Correct.
Because
Horizontal.
you equal it to 0, correct?
Well, if I look at this function up here, the one I've circled,
Yes.
I cannot have x be minus 1. That is a vertical asymptote.
Okay.
The only reason x equals 4 is not a vertical asymptote is because that factor got canceled out and it turned into a hole. In other words, if I didn't have an x minus 4 in the numerator up here, I would have two vertical asymptotes. I would have one at x equals 4 and one at x equals minus 1. But since this x minus 4 got canceled by this x minus 4, that turns into a hole, not a vertical asymptote.
Okay.
What's the horizontal asymptote?
The horizontal would be 1.
Y equal 1. Always remember your asymptotes are equations of lines. They're not a point. So it's not just 1, it's the line y equals 1, or the vertical line x equal minus 1.
Okay.
Okay. Now, our equation is x plus 4 over x plus 1. That's f of x. Next thing they're asking for are X-Intercepts. How do I get that?
For the X-Intercepts, wouldn't you have to equal the top to 0?
Okay. Was that
So then that would be -4.
okay? And that's the only one. About
The-
Y-intercepts.
For the y, you would plug 0 in for the x's.
Mm-hmm.
So then that would be 4 over 1.
And finally, holes.
Then for a whole,
Kind of have to go back to the original domain and function to find the hole. You're not going to be able to find the hole from this. That gives you no information about the hole at all. But if we go back to this, where's the hole?
the whole, wait, where is it?
Okay, to find the holes, we need to go back to the original function before we crossed anything out.
So it'd be -4.
Not -4. What makes that 0?
A 4.
4. In other words, it's in our domain. We actually don't have to look there. We can look at the domain to see that, wow, we can't be -1 and we can't be 4. I don't have a vertical asymptote at 4. Must have a hole at -4. Excuse me, at 4.
At 4, yeah.
All right, now we have almost everything we need to graph it. Okay, I'm going to graph it over here on the right. It's the first thing we should do.
We could draw out the holes so that you know where the lines are going.
Not the hole. It's hard to draw the hole yet. Start from the top and work down.
Oh, the asymptotes. The asymptotes.
Okay, where's the first asymptote?
The first asymptote, the vertical, that's -1.
Okay.
So you could go down, yeah, 1, and then make a line. And for the horizontal, you go up 1.
Okay. So that's kind of like a new grid. Now, I'm pretty sure, because I'm very familiar with, well, let's not be done with it. Where's the X-intercept?
The X-intercept is -4 and 0.
Well, right there, yeah, -4. I mean, when you say X-intercept, it means the second coordinate is 0.
0 automatically. Yeah.
The X-intercept is -4. Where's the Y-intercept?
4.
+4. So that's about right there. Hold on a minute. The Y-intercept, yeah. Okay, that makes sense. So, is my hyperbola in the first and third or the second and fourth?
It would be in the the second and...
Well, I call this one the first.
Okay, then the first and fourth.
Right, first and third.
Or the first and
These
third.
things are almost always diagonal to one another, especially when you have linear functions like this.
Yes.
So the fact that I know I cross the y-axis there, and I'm asymptotic to both of these asymptotes, means that's in the first quadrant. And this one must look like that. Notice how they're almost always diagonally opposite from the grid that you have drawn. And the last thing I need to put in there is a hole. And the hole is at 4, which happens to be where it was supposed to cross the y-axis. Well, it still does, but there's a hole there, like that.
Okay.
A good piece of information to know is that the graphs can never, ever cross vertical asymptotes.
So that's there. Okay, away from them. They never truly touch them.
They can cross horizontal asymptotes. It would be perfectly possible for this function to look like this. In other words, if I finish drawing that horizontal asymptote, it's possible for that thing to go on the other side and then come back to it, like that. So you can cross horizontal asymptotes. You can cross oblique asymptotes. Have you studied oblique asymptotes?
No.
They would be asymptotes that looked like this. In other words, they're neither vertical nor horizontal. And they only come about when you have a rational function where the degree in the numerator is exactly 1 greater than the degree in the denominator. And so far we haven't seen anything like that, but I was curious whether they... So we've done everything there is to do with this. We've graphed it and put the hole in it.
Okay.
Okay, describe the vertical asymptotes using limit notation. Well, in both of these next two questions, we're always using the limit of f of x. But when I'm looking at vertical asymptotes, I'm looking at as x approaches what from which direction?
It would be coming from the left. It would be infinity. or negative infinity
No,
approach.
going left to right. Where's the most important point when we're going left to right? It's that vertical asymptote. So it's as x approaches that vertical asymptote from the left. The vertical asymptote is at -1.
Yes.
We're approaching it from the left. What's that equal to?
Wouldn't it be negative infinity because the line goes down?
Correct. What is the limit of f of x as we approach that same asymptote from the right?
Infinity because it goes up.
Okay. And now they want the same kind of statements. What's the limit of f of x? But instead of approaching it horizontally, we're going to approach it vertically. In other words, we're going to look at end behavior. And end behavior is always as x goes to infinity or x goes to negative infinity. That's when you approach your horizontal asymptote. So what is this limit?
It would be x towards negative infinity.
What is
and that would be 1.
1. In other words, when I say what is the function approaching, I always mean what is the y value approaching. That's f of x. So I'm saying what does f of x approach as we go to infinity on the x-axis? Well, clearly it's going to this horizontal asymptote, 1. And what does it approach as we go to infinity on the left?
It would be 1 again.
Same thing. In other words, that is the definition of a horizontal asymptote. It's what the function approaches as x goes to either positive infinity or negative infinity. It's always going to be the same. In other words, this left part is always going to approach the same horizontal asymptote as the right part does, whether it's crossed it or not. If it's crossed it, it's going to come back and approach it. If it hasn't crossed it, then it's just going to approach it. Okay? So these limit questions that it's giving us are always the limit of f of x, but the difference is if it's a vertical asymptote, it's as we approach the vertical asymptote from the left and the right. If it's a horizontal asymptote, it's as x goes to infinity and negative infinity. And the answer is always going to be the horizontal asymptote. In other words, regardless of the function, regardless of whether I had graphed it or not, if I said, what is the limit of f of x as x goes to infinity, I'm going to answer that, because that's the horizontal asymptote.
Okay.
All right. So that takes care of that page. Let's see, did we have a second page? No.
No.
Okay, what would you like to do at this point?
I'll have another one. 1 second.
Yeah, if you want to send me more, we can do that. Or if you're...
1 second.
Okay.
This one's a little bit different.
And that's fine. Notice that we didn't have none on any of this.
Yeah, that's what I noticed as well.
But most functions, you would have no holes in them. In other words, if I make this x squared minus 8, then everything's pretty much the same, except I don't have any holes. I have 2 vertical asymptotes. I would have a vertical asymptote wherever the denominator was 0. So your holes turn into vertical asymptotes if you can't get rid of it by factoring.
Okay.
Okay. Did you send it yet?
Yes.
Oh, my desktop is filling up.
Yeah, I need to clean my computer too.
I know. I'm gonna clean it up once I switch operating systems.
Yeah, from Vista.
Well, yeah, there's no point in cleaning it up until I do that.
True.
Well, I mean, I guess there could be, but I'm gonna wait. All right. Stuff.
Yes.
This isn't really different. This looks to me exactly the same.
Lower down. Yeah, scroll down.
Okay.
This is a bit different. Um, at number 5 through 10, they're different.
Should we start
Yes.
there? Because I feel like we're just going to be doing the same thing here.
Oh yeah, up here it's the same thing, but
In
then
other words,
back
this factors into x minus 5 times x plus 5. This factors into x plus 5 times x plus 1. The x plus 5's cancel, leaving a hole. It's exactly the same process as we just did with the previous two problems. So
yeah.
since we only have 20 minutes left, let's do something new. All right, let's look at this one. Let's try to factor it. Does the top factor?
No.
No, it does not. Does the bottom factor?
X plus 2, x minus 2.
Yeah, they tried to fool us by putting the x squared behind it.
In the wrong notation.
What's that?
Form. In the wrong form. Or out of standard form.
Okay. So what's the domain? Notice that I can't cancel anything.
Correct.
How many vertical asymptotes do I have?
Would we have 2?
Correct. At 2 and at minus 2. Any other restrictions on the domain?
No.
Okay, so what is it?
Negative infinity to negative 2. Then from negative 2 to 2, and then from 2 to infinity.
And you understand the difference between parentheses and brackets?
With brackets, it's like right there on the graph.
If that was a bracket, it would mean that it would be okay to be minus 2. But it isn't okay. So it's got to be a parentheses. Okay. A problem that might have a bracket would be this function. The domain of this function right here is a bracket 0 to positive infinity, parentheses. And the reason it's a bracket is because it can be equal to 0. Just can't be negative. So I would show the interval notation for the domain like that. So far, every problem we've seen, no brackets, because we haven't had this kind of a function yet, where it can actually be equal to 0. It just can't be less than 0. So this is correct, all parentheses. And let's see, what else do they ask? Find each function's domain and equations of its vertical and horizontal asymptotes. Okay, so vertical asymptote. What were they?
For the vertical, that would be 2 and -2.
Correct. And the horizontal?
And horizontal, it would be 2.
It's a ratio of the coefficients. Remember what this started out as. X squared plus 3x minus 1 over x squared minus 4. Look only to the variable that has the highest degree. Nothing else matters for horizontal asymptotes.
Then it would be 1.
Y equal 1. And let's see, what else do they want? That's it? Find each function's domain and equations of its vertical and horizontal asymptotes. All right, it would be worth doing one other thing here before we leave this problem, and that's graphing it, at least trying to see what the graph might look like. There's 2 vertical asymptotes. So this doesn't divide the grid up into quarters. It divides it up into whatever you want to call this. And there's a horizontal asymptote there. Okay? So that's my grid that I'm going to operate on. And usually the way these look is got my hyperbolas there, got my hyperbolas there, and maybe in the middle it does something like that. Okay? It can do various things. It can do that in the middle, or it can go up and turn around and come back down, and this part comes out from the top. In other words, I would have to do more work to graph it. My vertical asymptote and my horizontal asymptote alone do not allow me to graph it. From that information, I can't graph it.
Okay.
I can guess what it might look like, but I can't tell if it crosses this horizontal asymptote. It might. And the way to tell would be to try to solve that equation by setting y equal to 1.
Okay.
Okay? And it does cross it. In other words, if I want to know, we can find the X-intercepts and the Y-intercepts in the same manner that we found them before. But that might not help me either. I really need to know what's going on between these 2 vertical asymptotes. And so it would be nice to know, does it cross this horizontal asymptote? Well, what would it take for it to cross that? That asymptote is at 1. I'm saying that the y value would be 1. In other words, can I solve this equation? If I can, it can be that. If I can't, it can't be that. Well, I can solve that equation. Multiply both sides by x squared minus 4. Now that's equal to x squared plus 3x plus 1. The x squareds go away. I've got 3x equal minus 5. So I'm saying that when x is at 5/3, minus 5/3, which is about there, it's crossing that horizontal asymptote.
Okay.
If it did not cross the horizontal asymptote, I would not be able to solve that equation. It would be an equation such that it would not have a solution. And then I would know that it doesn't cross that horizontal asymptote. Knowing that it crosses this horizontal asymptote allows me to pretty much figure out how to graph it in between. In other words, it's probably almost certainly going to do something like that in between, which means it does that in that quadrant, and it does this in this quadrant. So if I graph that on Wolfram alpha, guarantee it's going to look exactly like this.
Okay.
So on all of these is all they want is the domain and the asymptotes. Give me the short version of the domain without giving me interval notation on 6.
The domain.
Uh-huh.
I believe it would be, you couldn't factor it on the top.
No, you can't factor. Oh, yeah, actually, no, you can't. That's an x cubed.
So what I could do is x minus 4 equals 0.
That's it. That's the only domain restriction there is.
Okay.
So what is the domain? The short when I say the short version, it's the following. X can be all reals except 4.
Okay.
It's a little shorter than interval notation, means the same thing. And you write it like this. X, technically you write it like this. X such that X can be equal to all reals. X not equal to 4. I just end up saying X can be all reals except 4.
Okay.
Okay. Vertical asymptote?
Say that one time, please.
Vertical asymptote on number 6.
Would that be 4 as well?
Correct. It's not just 4, it's X equal 4.
Equals 4.
In other words, it's a vertical line, and it needs an equation for a vertical line. Okay.
Okay.
Horizontal asymptote.
My teacher taught if the top equation is top heavy, there isn't one. And if it's bottom heavy, it's 0.
Finally get a none. Well, not quite. If it's bottom heavy, it's 0. If it's top heavy, there is none. There's a difference. A 0 asymptote looks like that. No asymptote looks like this. No dotted line at all. In other words,
Okay.
no universal end behavior as X goes to positive and negative infinity. So none is the correct answer, not Y equals 0. Now, this is X to the third over X. If that were X squared instead of X to the third, I can divide this into that, and it produces an oblique asymptote. But if it's X to the third, oh boy, you really need to divide it anyway. And then deal with the remainder. Yeah, I still think that there's no horizontal asymptote there. Okay, let's look at 7 rather than getting hung up on that. Because 7's a little different. It's a lot different, actually. We might have just enough time to talk about it. What's the domain restriction?
For which one? 7?
Yeah.
It's bottom heavy.
Okay. So the horizontal asymptote is X equals 0, or Y equals 0, right? But let's talk about domain. What affects the domain?
You have to make the denominator equal to 0. So x cubed minus 9 equals 0. So you can cube root it.
X cubed equals 9. Take the cube root of both sides.
That's 3.
No, it isn't. The cube root of 9 is the cube root of 9.
Okay.
Okay? In other words, the square root of 9 is 3.
Oh, okay. Yes.
The cube root of 9 is not 3. Now, I can factor that. I don't need to. But I could, because it's difference. Oh, no, I couldn't. It's not difference of perfect cubes. No, I was thinking it was difference of perfect cubes. No, we do exactly what I did here. We just set it equal to 0 and solve. Okay, and that's not a plus or minus either. That's a plus only. If x cubed is equal to 9, then x is equal to plus cube root of 9, not minus. You only get the plus or minus is when you have an even power.
Okay.
If it was x cubed equals minus 9, then that's x equal minus the cube root of 9. So when you have odd exponents that you're solving for, you only get one answer. You don't get a plus or minus answer. So,
Okay.
vertical asymptote is what?
The vertical asymptote would be cube root of 9.
That's it. X equal that. In other words, that actually is the definition for the vertical asymptote. X equals cube root of 9. Horizontal asymptote?
The horizontal asymptote would be 0 because it's bottom heavy.
Y equals 0. All right. What's the horizontal asymptote on 8?
For 8, it would be 2 because it's
Y equal 2.
yes, y equals 2.
What's the vertical asymptote on 8?
X would equal 2 after you equal the x minus 2 to 0.
And what's the short explanation for the domain?
Oh yeah, that would be like the little bracket symbol thingy.
All reals, well, yeah, you can just say all reals except x equal 2.
Okay, all reals
That's the only restriction. These restrictions always come from the denominator, not the numerator. In other words, I have no problem dividing into 0. Okay?
Okay.
I noticed something on 8 that I didn't notice before. 8 factors. Ooh, almost did 8 wrong. I can factor a 2 out from the top.
It's going to be x minus 2.
Yeah. What does that change?
It'll just be 2 by itself after you cross out the x minus 2.
Do I have any vertical asymptote?
Yes, that would be 2.
No. It disappears. It becomes a hole. Remember that when it crosses out, I now have a hole at x equal 2. Because it's still a domain restriction. My domain is still all reals except x equal 2. Just because this thing turns into 2 doesn't eliminate that domain restriction.
Okay.
So I have no vertical asymptote, but I have a hole at x equal 2. So this function, f of x equal 2, is a horizontal line with a hole right there.
Okay.
So always check to see if you can factor it. I mistakenly saw that none of these appear to factor, such that you can cancel stuff out. But I was wrong, because this one does. What's the vertical asymptote or the domain on 9? Quick version.
All real numbers except 4.
What's the vertical asymptote?
The vertical asymptote would be 4.
X
equals 4. X equals 4.
Now what's the horizontal asymptote?
That would be 0.
Y equals 0.
Y equals 0.
Okay. What's the restriction on the domain?
All real numbers except -3.
What's the vertical asymptote?
The vertical asymptote would be -3. Or x equals -3.
What's the horizontal asymptote?
Y does not exist.
Well, it's not really a does not exist. There's no horizontal asymptote. That's
No horizontal.
it's not quite the same as does not exist. Does not exist is a term that tends to be used in place of infinity.
Oh.
Okay? So if the horizontal asymptote doesn't exist, then it's none, which is not the same as y equals 0. Notice that if this were the denominator and this were the numerator, we would have a horizontal asymptote at y equals 0. But there's none with this.
Okay.
The fact that I can factor the top doesn't help. I can factor an x out, doesn't change anything. All right.
Okay. Thank you.
You're welcome. Talk to you next time, Taylor.
Thank you.
Bye-bye.